Stokes' theorem. Recall Green's theorem. Let R be a simply connected plane region with boundary a simple, closed, piecewise smooth curve C oriented counterclockwise. If f of xy and g of xy are continuous with continuous partial derivatives on some open set containing R, then the line integral over C, f of xy dx plus g of xy dy is equal to the double integral over R, partial g with respect to x minus partial f with respect to y dA. Note that if f is the vector field little fxy I plus little g xyj, then the curl of f is the determinant that in the bottom row has f, g, and 0 as components because the k component of the vector field f is 0. So that's equal to 0 minus 0 I plus 0 minus 0 j plus the partial of g with respect to x minus the partial of f with respect to yk. Right? So notice that if we multiply the integrand of the double integral by k, we get the curl of f. This means that the equation in Green's theorem can be written as the line integral over c f dot dr is equal to the double integral over r curl f dot k dA. We're now going to generalize this result to vector fields and surfaces in 3 space. So Stokes' theorem says the following. Let S be an orientable, piecewise smooth surface that is bounded by a simple closed, piecewise smooth curve C with positive orientation, and let F be a vector field whose component functions have continuous partial derivatives on some open set containing S. Then the line integral over C f dot dr is equal to the surface integral over S curl f dot ds. The most important part of this theorem is the equation given there. Everything else is just all the technical information that will allow the theorem to be true. Nonetheless, let's review the terms that appear in this theorem, and there's also one new one that you haven't seen before. So starting with orientable, remember that that means there is a function little n such that for each point x, y, z in S, n of x, y, z is a unit normal vector to S at x, y, z, and n varies continuously over S. A surface is smooth if there is a parametrization R of u v of S such that R sub u cross R sub v is never 0. Piecewise smooth means that the surface can be split up into finitely many smooth pieces. A curve is closed if its starting point and ending point are the same, and a closed curve is simple if it does not intersect itself. A curve is smooth if there is a parametrization R of t of c such that R prime of t is never 0. And piecewise smooth means that the curve can be split up into finitely many smooth pieces. Finally, this one's new. So by saying that the piecewise smooth curve C has positive orientation, one way to think of this is that if an animal is walking along the curve with their head pointed in the direction of the orientation of the surface, in other words, the normal vector function, then the surface will always be on the left. Here's a picture of a curve with positive orientation with respect to the orientable surface. Right, so notice that the normal vector in this case is pointing upward and the curve is moving counterclockwise because if you move along the curve with your head pointed in the direction of those normal vectors, then the surface will always be on the left. Let's try an example. Go ahead and pause the video, try this example yourself, and then resume the video to check your answer with mine. Evaluate the line integral over C f dot dr, where C is the curve of intersection of the cylinder x squared plus y squared equals 1 and plane y plus z equals 2 oriented counterclockwise when viewed from above. And the vector field f of xyz is equal to negative y squared I plus xj plus z squared k. As always, we should start by drawing a picture of the situation. Notice I drew the cylinder x squared plus y squared equals 1. And I sliced that cylinder with the plane y plus z equals 2, or equivalently, z equals 2 minus y. Notice how when the plane slices the cylinder, it creates a little distortion there, as usual. Notice that I also drew a picture of the circle x squared plus y squared equals 1 in the xy plane. You could see that is the intersection of the cylinder with the xy plane. So now we're going to apply Stokes' theorem to compute this line integral, which means that we're going to compute the surface integral instead. So first we'll need the curl of f. So to compute the curl of f, we put ijk, the three partials in the second row, and in the third row, we put the components of the vector field, negative y squared x and z squared. So when we do the I component, we get the partial respect to y of z squared, which is 0, minus the partial respect to z of x, which is 0. For the j component, we get the partial with respect to z of negative y squared, which is 0, minus the partial with respect to x of z squared, which is 0. And for the k component, we get the partial with respect to x of x, which is 1, minus the partial with respect to y of negative y squared, which is minus 2y. So 1 minus minus 2y is 1 plus 2y. So the curl of f is just 1 plus 2y k. Now, next, we're going to need to find a normal vector to the surface. First, I just want to make sure that it's clear that the curve of intersection of the cylinder and the plane is the upper part of that cylinder where the plane is slicing it. So the corresponding surface lies on the plane. It's that closed region that's bounded by the upper part of that cylinder that is inside of the plane. So a normal vector to that surface is also a normal vector to the plane. So let's let g of xyz equal y plus z minus 2. In other words, I'm taking the equation of the plane and bringing everything over to one side of the equation. Then the normal vector that we're looking for is just the gradient of g, which is just j plus k. We want the normal vector that's pointing in the upward direction because we're given that the orientation of the curve is counterclockwise when viewed from above. So in order for the surface to be on the left, we need to use the upward normal vector. Okay, now we're ready to compute the surface integral. The surface integral curl f dot ds. By definition, this is the surface integral over s curl f dot little n ds, which we could change to the double integral right away by taking the double integral over r curl f dot capital N dA, which in this case, we're just taking the curl of f dotted with the gradient of g. Since curl f only has a k component, we're just multiplying 1 plus 2y times 1, because the coefficient of k in n is 1. So inside the double integral, we just get 1 plus 2y. The line integral over c f dot dr by Stokes' theorem is the surface integral over s curl f dot ds, which we just found to be the double integral over r 1 plus 2y dA. We'll do this double integral in polar. Notice that the region is that disk that I drew earlier. So theta is going from 0 to 2 pi, r is going from 0 to 1, and we replace y by r sine theta. So we get 1 plus 2 r sine theta in the integrand. And since we're changing to polar, we multiply by that extra factor of r as always. Distributing the r, we get r plus 2r squared sine theta. Doing the inner integral, we get r squared over 2 plus 2r cubed over 3 sine theta from 0 to 1. Plugging in the 1 gives us 1/2 plus 2/3 sine theta. Plugging in the 0 just gives 0. Integrating with respect to theta, we now have 1/2 theta minus 2/3 cosine theta from 0 to 2 pi. So we just get 1/2 times 2 pi plus 0, because the cosine of 2 pi and the cosine of 0 are the same. So the final answer is pi. Let's do an example going the other way. This time we're being asked to evaluate the surface integral of curl f dot ds. So to use Stokes' theorem, you'll change that to the corresponding line integral. Go ahead and pause the video, try this example yourself, and then resume the video to check your answer with mine. Evaluate the surface integral over s curl f dot ds, where f of xyz equals xzi plus yzj plus xyk, and s is the part of the sphere, x squared plus y squared plus z squared equals 4, lying above the xy plane and inside the cylinder x squared plus y squared equals 1. Let's start by drawing a picture. Here's a picture of the part of the sphere, x squared plus y squared plus z squared equals 4, lying above the xy plane. So it's a hemisphere. It's just the upper part. And here's the cylinder, x squared plus y squared equals 1. So the intersection of that sphere and cylinder we could get by replacing x squared plus y squared by 1 in the equation x squared plus y squared plus z squared equals 4. Subtracting 1, we get z squared equals 3, or equivalently, z equals the square root of 3. We only take the positive square root because we're above the xy plane. Now, instead of using that surface, we could use the bounding circle. So to compute the line integral, I'm going to start by parametrizing that circle. The most natural parametrization for that circle is r of t equals cosine ti plus sine tj plus root 3k, where t is between 0 and 2 pi. Right? Cosine ti plus sine tj is standard parametrization for a circle, but it's plus root 3k because z is equal to root 3. That circle is sitting root 3 units above the xy plane. So r prime of t is negative sine ti plus cosine tj. And f of r of t, we replace x by cosine t and z by root 3 to get cosine t times root 3 for the I component, or equivalently root 3 cosine t. Similarly, for the j component, we get root 3 sine t. And for the k component, we get cosine t sine t. Now we're ready to compute the surface integral. We change it to a line integral using Stokes' theorem. So we get the line integral over c f dot dr, which is the integral from 0 to 2 pi of the dot product of f of r of t with r prime of t dt. Now, when we take that dot product, we get root 3 cosine t times negative sine t, or negative root 3 cosine t sine t, plus root 3 sine t times cosine t, or root 3 cosine t sine t. Those two terms actually add up to 0. So we just get the integral from 0 to 2 pi 0 dt, which is just 0.